So for the review session today, Tian Tian, you saw her before. So she's going to help us again to review the questions you were given on the e-class. But if there's any follow-up to any of the questions there she's going through, you can also ask. That's okay. So we can definitely answer them as well. If there's anything you want to ask directly to me, you can also say that. Otherwise, Tian Tian will be in charge today. But I'll be here as well. Okay, go ahead.
Hello, welcome to the review session. I'm basically just going to be going over the questions in the practice test. So let's start with the first one. If you recall from your practice test, or if you have it pulled up right now, basically it gives some class definitions for point V1 and point V2. And then it gives a few lines of code, and it asks after these lines of code execute, what is going to be the result of these assert statements. So basically, after we execute the code that was given, you would have this in your current context. So we have P1 pointing to point V1, P2 and P5 pointing to point V1, another point V1 object, and so on. So then it asks you to evaluate whether or not these statements are going to fail. So basically, for assert same and assert not same, the important part to remember is that we're testing is A double equal sign to B, which just means is A pointing to the same reference or the same object as B. And then the important part for assert equal and assert not equal is we're testing if A dot equals B is true or false. So let's go over a few of the examples. I'm not going to go through all of them just for the sake of time, but for example, doing A, we're testing assert not same P1 and P2. So what that would just be testing P1 equal P2. And we're checking if this is true or false. So we have this. And in this case, we see that P1 here is pointing to a different object than P2. So this would be false. And because they're not equal, assert not same is going to pass. So this would be a pass. So we're not going to select it because it's asking which ones are going to fail. And then for B, we're testing is P4 equal to P6. So let me just erase this. Testing P4 equal P6. And in this case, we see that P4 is pointing to this object here, and P6 is also pointing to this object. So in this case, it's true. So assert same is going to pass. So we'll put a check mark here, and we're not going to select that. Now let's also do assert equals. So assert equals is checking P3 dot equals P4. Okay, and then in this case, in the class definitions, you'll see that for point V2, there is an overridden equals method, which just means that we're checking not only if the objects are the same, but also if the X and Y values are the same. However, we also need to keep in mind that P3 and P4 need to have the same classes. So you just need to check the method definition, but basically what it's doing is it's first checking is P3 and P4 pointing to the same object. If it is, it'll return true. But if it's not, we're going to then check is P4 pointing to null. And in this case, P4 is not pointing to null. So we're going to then check, do they have the same classes? And in this case, they do have the same class. So then finally, we check, are their x values and y values the same? So in this case, x values and y values are the same. So assert equals is going to pass. So this is also a check mark.
So what Tian just described were the four phases that we talked about in the class for equals method. So in this practice test, I just gave you the version you're familiar with in the point V2. So in the actual test, I could be maybe giving you just the same version, or maybe I can modify maybe the version a little bit. So always remember when you trace the assert equals, it's always going to be argument 1 dot equals argument 2. And then which version of the equals is going to be called dynamic binding. Look at the dynamic type for the context objects. Always remember that. Okay.
Okay, so I'm going to leave the last two for you guys to do on your own, and I'll just move on to the next set of questions. So continuing on, we have the other assertions. So let's try F. For F, we're doing P1 dot equals P2. Okay, so our context object here is P1, which is pointing to this object, which is of type point V1. And in the code that was given, you'll see that that one doesn't have the overridden equals, so it's just using the default object equals method, which is just checking if the references are the same. So, or if the references are pointing to the same object. So in this case, P1 is not pointing to the same object as P2. So this would actually fail. So assert equals here is going to fail. So we would select this one. And then let's do one more. Let's try assert not equals. So we're looking at H over here. So this one, we are checking, one second, let me switch to the pen. Okay, so this one we're checking P3 dot equals P4. However, because this is not equals, we need to see if this evaluates to false. And for this one, P3, the context object, is this point V2 object over here. So we know we have the overridden equals method. And then P4 is pointing to this one, which is of the same class. So in this case, P3 dot equals P4 is actually going to be true. However, because we're checking if it's not equals, this is going to fail. So this one is going to fail, and we would select this one as well. Does that make sense so far? Okay. So I think that's about it for assert equals and assert same. I'm going to move on to the inheritance stuff now.
Just before, I was just curious. So guys, take a look at option G. Why would this assertion fail? Because if you look at P4 and P6, according to the diagram in green, P4 and P6 point to the same objects. So why would this fail?
Because it's checking for the opposite. That they
Aha, exactly. So be careful. So when you look at the assertion there are at least there are four possibilities. It could be assert same, assert not the same, right? In this case, assert not the same are really expecting the two references to be different. But in this case, the two references are the same. So that's why it should be failing, right? Always look at the assertion first to see what exactly you're checking, okay? Yeah.
Okay, so for the rest of the questions in the practice test, it's basically just based off of these classes. So the first thing you want to do is just draw the inheritance diagram or the hierarchy to get an idea of which classes are, or how classes are related to other classes. So I'm going to draw it with you guys. There's two methods you can kind of take to doing this. First is to just see which one is the top class, so which one is not extending anything. And then you start from the top, and then you draw it downwards. Or you can just go class by class. I'm just going to go class by class for this. So what I mean by class is just you do the first one, then you do the second one, and so on. Just do whichever one you feel more comfortable with. But basically, we have class A extends B. So what we're going to draw is A, and then extends B. What you can think of this as is you draw an arrow upwards. So it's like extending upwards. And then we have B up here. So A extends B. I'm going to move it down a little bit. Okay, next we have B extends C. So we already have B. We'll draw extends and then C. And then we have class C, which is already here. So let's look at the next one. Class D extends C, so let's draw D over here, and then it extends C. And then we have F extends D. So we have F, and same thing, go up to D. And then E extends F. So finally, we have E over here, and then extends F. And also, I would recommend to just make a note of what methods are in each one. So for example, like BM and EM, what I would do is just write on the side, F has BM and EM, E has DM, D has CM, and C has BM. So this is just helpful when you're doing the questions to know which classes have which methods. Okay, so let's move on to the actual questions now. So I have just the same diagram, but a little bit smaller on the side. So the first thing in the questions that you'll see is we're just evaluating some code line by line. So this here is the first line that we have to evaluate. So the question is, does this line compile? So to check whether or not this line compiles, we're going to first look at the dynamic type here of the object we're creating. So this is dynamic type, is C. And we're going to look at the static type of the variable. So here we have static type D. And the question we want to ask is the dynamic type a descendant of the static type? Which is also equivalent. You guys have probably learned this in class. Let me just move this over a little bit. So this is one way of asking. This is equivalent to asking, can the dynamic type fulfill the expectations of the static type? So these two are basically equivalent. For me personally, I prefer just using this one because it's easier to just check whether or not something is a descendant. But if you're more comfortable with this, of course, you can use that as well. So let's look at the dynamic type. Dynamic type is C. And what about static type? The static type is D. So is C a descendant of D? C is here, D is here. So you can see that C is not a descendant of D, which means that this code is not going to compile. In the same way, you can say that C, because C is an ancestor of D, C may not be able to fulfill all of the expectations of D, because D might define some additional methods. So in that case, again, it will not compile. So here we will say that this does not compile. And what's the result? We just have a compilation error. So this doesn't compile. Let's move on to the next question. Okay, so here we have the same situation. We're assigning a new object to some variable. And again, we're going to ask the same question. Look at the dynamic type, which is D. going to ask, is the dynamic type a descendant of the static type C? So D is over here, and C is over here. So D is a descendant of C. And in other words, D can fulfill the expectations of C. So this is going to compile. And the result, what we can do is we'll just trace out what happens with this line. So what we'll have is a new object of type D. And then we have C, D2, pointing to it. So this is our result here. Okay, so I'm going to copy this just so we have a reference to what's happening, because we need the context for the future questions. So let me just paste that over here. Okay, now we're going to ask about method calls. So first, we need to check if it compiles. To determine if a method call is going to compile, we again need to check the static type. So for compilation, we always want to check static type. So our static type of D2, if we look over here, is C. And what we need to ask is, does C have the method BM defined? Or do any of the ancestors or additional ancestors of C have BM defined? In this case, C doesn't have an ancestor, or other than itself, because C is an ancestor of itself, but it doesn't have additional ancestors. However, let's say there was another class up here with BM, and say BM wasn't defined in C. C, we could still call BM on an object with static, or on a variable with static type C, because we expect C to be able to have that method, because C can fulfill the expectations of its ancestors. But again, in this case, BM is just defined in C, so we will say that it compiles. So it does compile. And then what's the output? So if you guys recall dynamic binding, we basically need to check the dynamic type of the object in order to determine what version of the method is going to be called. So what is the dynamic type of D2? If we look over here, we have dynamic type D. So we want to look starting at D. Okay, so we start at the dynamic type, and then we're going to check, does it have BM in it? It doesn't. So let's move up a level to the next ancestor. We're going to check, does it have BM? It does. So this is the version of BM that's going to be called. So our output here is going to be C.BM. And this output is like stated inside of the class definition. So if we go back here, yeah. So make sure you always check the code that's given to you. But in this case, we're printing C.BM. Okay, so let's move on to the next one.
Yeah, quick comment. So whenever you want to look for the overridden version to call, you want to look at the version that's in the closest ancestor, which might just be the class itself. Okay, if the class itself does not override the method, you go up one level to find which is the closest one. Okay, just remember, yeah.
If the static method had been D, it wouldn't be able to get it, right? Because the static type is
Okay,
the
so
one that...
to go back. So sorry, what did you want to change?
No, I'm just wondering if the static type was D, it wouldn't work, because the static type is the one that like...
Yeah, that's correct.
Which method.
Yeah, you're asking if hypothetically if D2 was declared statically of type D. So in this case, yes, you wouldn't be able to call BM because D itself has no expectation for BM. BM only, oh, actually, no. So here, let me see it again. So if I change maybe the static type of D2 from C to D, in this case, D, you can see it's going to inherit BM. right? So BM is still part of the expectation for D,
Okay.
right? So remember the exercise we did in class. Whenever you want to work out the expectation for a particular class, you have to accumulate the expectation for all the ancestors all the way to the top, right? So in this case, even if you change the static type for D2 to D, you can still call BM. Yes. Okay. Yeah.
Okay. So this one is again just a variable assignment. So we're doing the same thing as before. We're checking our dynamic type and our static type. So we're asking, is E a descendant of D? So E is here, D is here. So E is a descendant of D. So this is also going to compile. And then the result, we'll trace it as well. Let me just grab this from here so we know everything that's happening. Okay, so this is our current context. And then we also want to add an object of type E. So we'll put this over here. And then our variable is of static type D. And then we'll point it to our new object of type E. Okay, so this question is done. I'm going to, again, just copy this so we have reference to it later. Okay, so now we're doing another variable assignment, but this is a little bit different because we're not creating a new object. We're just reassigning a variable to, or we're reassigning an object that's referenced by a variable to another variable. So here, we want to look at the static types for compilation. So we want to check the static type of E1. And we see here that it has static type D. And then we also want to check the static type of D2, which has static type C. And now the question that we want to ask is the static type of the right-hand side a descendant of the static type of the left-hand side? So it's the same as with having a new object. We're again checking if the right-hand side is a descendant of the left-hand side. But in this case, we're just considering the static type. So is D a descendant of C? It is, so this is going to compile. And then the result is that we're going to point this arrow here over. One second, let me just move this over a bit. Now D2 is going to point to the object that E1 is pointing to. So this goes here. Okay. So this is what we have so far. Now the next line that we need to check is this one. So it's again a method call. This time it's a little bit different because remember D2 has been reassigned. So it's different but also kind of the same. Basically for compilation we want to check again the static type. So our static type here is still C. So we know that BM is defined in C, which means that this is going to compile. But what is the output? So again, for our output, which is runtime behavior, we want to check the dynamic type. So the dynamic type of D2 now is E. So what we're going to do based on dynamic binding is we're going to start here at E and we're going to check, does it have BM defined? If it doesn't, we'll go up to the next ancestor and check, does it have BM defined? In this case, F does have BM, so we're going to call the version of BM that's in F. So if you look at the code that was given, the output of this is just going to be f.bm. So again, we're always going to call the method that's in the closest ancestor of the dynamic type. Okay, let me just grab this one more time. Okay, so this is another situation that we've seen before. We're just assigning a variable to another one, to another variable. So we're checking the static types. So the static type of E1 is D, and the static type here of F1 is F. So we want to check, is the static type on the right-hand side? Yeah, question?
The last question.
Mm-hmm.
How do we to cast to D2?
Sorry, what do you mean?
Like, if you want to call .bm from F, do you not cast?
Patricia, are you referring to this page or maybe the last page?
D2.bm.
Oh, you mean this line here? Okay, so as Tintin said before, whenever you look at a method call, so to see if that will compile, look at the static type for D2, in this case, the context objects. So D2, you can see that was declared statically as C. That one never changed. Static type remains the same. So now we ask about, does C have the expectation of BM? It does. If you look at that, C does have BM, so this will compile.
So wouldn't the output be C.bm?
So, okay, so output then is going to look at the dynamic type. In this case, D2 is pointing to E objects. So E will be the dynamic type, which will be the bottom of the hierarchy. But I can see that E itself does not override BM. So we're going to go up one level. We can see the ancestor or parents of E, which is F. That one does have BM. That's the closest one we can get to. So we don't go any further back to the version in C, because we already found the closest version in F. Right? Make sense to you? Yeah. So you only have to do the typecast if maybe the static type itself is not specialized enough. So you may want to do some downcast sometimes, but I gotta watch out for class cast exception, of course, whenever you do downcast.
Okay, let's continue with this one. So again, we're checking if the static type of the right-hand side is a descendant. So right-hand side is a descendant of the static type of the left-hand side. So is D a descendant of F? It's not. So this is not going to compile. And since it does not compile, it never runs. So we don't have to worry about that. Okay, next page. So now we have another method call. So to check if it compiles, we want to look at the static type again. Our static type of E1 is D. So we want to check, does D or any of its ancestors have the method EM defined in it? So D doesn't have EM, C doesn't have EM, which means that this will not compile. However, if we look at the actual object over here, it's of type E. And E is a descendant of F, which does have EM. So we actually have E, we expect E to be able to call the method EM. So how can we actually do this method call? What we can do is a typecast. So let's look at the typecast over here. So what we might be thinking is F has EM defined, so let's just cast to F. Let me also paste this over here. Okay, so we can try to cast to F. However, does this line compile? The issue here is that the method call is always going to have, I guess, the higher, what's it called? The higher precedence. Yeah, higher precedence. So it's going to do the method call first and then the cast. But the issue is, as we said before, E1 has static type D, which does not have EM defined. So that's not going to compile. And what we're trying to do here is also we're trying to cast a method call which doesn't really make sense. So what we need to do is add brackets. So we're going to add brackets over here. And now let's see if this will compile. So to determine if a typecast is going to compile, we want to check if the static type of our variable is either an ancestor or a descendant of the cast type. So we have E1 with static type D, and our cast type is F. So is D an ancestor or descendant of F? It is, because we can just travel along some straight line down to get to F. So D can just go down to get to F. So in this case, we're doing a downwards cast from D to F, and it's going to compile. So it will compile. And I guess before you can conclusively say that it compiles, we also need to check to make sure EM is expected from a variable of type F. But in this case, we know that it is. So yes, the whole thing is going to compile. And then what is the output? What we're doing, so we're going to start from the typecast. What's happening is when we perform the typecast, we're making an alias of type F. So we have F, E1, and it's going to point to the same object that E1 is pointing to. And then we're going to call the method basically on this alias. So what's the dynamic type that the alias is pointing to? It's E. So we're going to do the same thing again. We're going to start at E. We're going to check, does it have EM? If it doesn't, we go to the next ancestor. Does it have EM? It does. So we're going to call f.em. So our output here is going to be f.em. Okay. So this is the last question in the practice test, but I have some more examples just to get you guys more familiar with typecasting.
Yeah, Tintin, just before you continue, any questions so far about, go ahead.
So in the last slide, you did F, you casted F. Does this still work if you cast E? Because I assume E inherits EM, right?
Yeah. Yeah, E will inherit EM, so if you cast it to E, it would also work.
Yep, it's a good question. So Tintin can write it down too. So that's definitely one alternative. Yeah, for sure. So one thing you also got to remember, so in this case, we're using anonymous cast. It's like a cast without any name. So especially, I'll just point very quickly. Yeah. So just remember, let's say here, if you look at just this expression here, the static type for this expression will just correspond to the cast type. From that cast type, you can decide what will be the expectation. Will that include EM? It does. So that's why it will compile. Okay, just remember that.
Okay, so let's continue from here. So let's say that we decided to define the method EM in the class A as well. So this wasn't there before. We just decided to add that. Can we cast to A in order to call EM? So what we want to do to check if it compiles is, again, first check the static type of E1.
And Tintin, can you put the diagram again
yes.
back? It'll be easier for us to see.
Yes. I'll grab this. And then I'll just paste it over here. Okay. So our static type of E1 is still D, because the static type doesn't change. And then we want to check, is the static type of E1 an ancestor or descendant of A? So our static type is D. Is it an ancestor of A, or is it a descendant of A? It isn't, because we have to go up and then down. So like a way to check if something is an ancestor of something else is, can we draw like a straight line down to get to it? And if it's, to check if it's a descendant, we can see, can we draw a straight line up? But in this case, we have to go both up and down. So it's not an ancestor or a descendant. And because it's not an ancestor or descendant, it's not going to compile. Okay, so this is done. We have one more example that I wanted to share. Gonna grab this again.
So Tian use the next page. Sorry, just go back here.
Oh, okay. Here?
So did you plan any page to see how we can make this work to compile? Not
no,
really,
but
right?
I could talk about it.
Okay, how about this? Okay, let's do this. So guys, remember the exercise we did, the last one, right? I forgot the slide number. Was it 67? Something like that, right? So question for you. So apparently you can, E1 static type is E. You cannot cast from E to A, right? How can we make it work? Is it possible to write let's say you can get an unlimited number of casts, but can we somehow make some casts to cast from E to A?
Can you cast to C first? Like cast up to C and then cast to
Yeah, that's exactly what we said, right? You basically want to cast to something high enough so you can downcast again, right? So Tian can write it down just to say upcast first and then downcast. And then we'll go from there, okay? So this is basically what we discussed it's the last example on the slides. Okay, I'll just do in a different context just to reaffirm. Okay. And meanwhile, so while Tian is writing it down, so apparently we're trying to do upcast first and then downcast to make it compile, which is good. And the next question is, if that compiles, what's going to happen at the runtime? Are we going to pay some price about running into class cast exception? If so, since we're doing upcast and downcast, which cast is going to give us the class cast exception? Right? Think about this one first, and then we're going to make it clear. Right? Okay, that's good. So anyone want to try? Are we going to run into class cast exception at a runtime? Oh, go ahead. Yeah. Are we?
Yeah. So,
What's the reason?
so the first cast to C would work, but the cast to A wouldn't work because it's E is not a descendant of A, like as the dynamic type.
Ah, perfect. So here, so Tian can first highlight the first typecast is go from E1 to C, right? So this one here basically is really trying to do an upcast from E1 static type is actually D. So from D to C, there's a valid upward cast, right? In which case you're asking whether the dynamic type of E1, which is E, can E fulfill the expectation of the cast type C? Indeed, because E is a descendant of C. Okay. Let me just do it a little bit. Yeah. Let me just, yeah. Okay, very quickly. Let me just do a little bit. Okay. So if you look at this one here, so E1 has the static type D, and we're casting that to C. So from D to C, we're doing upward cast. Compilation is good. And then what about dynamically? Dynamically, E1 is pointing to E right here. So can E fulfill the expectation of C? It can, right? So this cast over here, the first one is going to compile, and there's no class cast exception. Okay, that's good. And then this cast expression here, okay, so let me just do a little bit more. This cast expression here has the static type corresponding to the cast type, which is C. So now the second cast is going from C to A. So from C to A, compile is downward cast. Okay, good. What about dynamically? So now we're basically asking E1, which still pointing to the same object. We never redirected. In that case, we are having E. Can E dynamic type fulfill A? Can E fulfill A? No, it cannot. So we still got to pay the price of class cast exception. All right. So this one here is really the second one that's going to give us class cast exceptions still. Right? You can revisit maybe what we did in that exercise in the last slide that we spoke about for typecast. It's really the same issue here. Okay. You want to know exactly where we got the class cast exception. Okay.
Okay, should I move on to the next
Yeah,
one?
please.
Okay.
Yeah.
So last example for typecasting. Let's say that we decided to create a new class called G, and we're making it extend F. So let's say we want to make a variable as well of static type G, and we want to assign it to E1. And we decided to do a typecast in order to do that. So we want to know, does this line compile? So first, we always want to check the typecast to see if that compiles. So again, to check if it compiles, we're going to look at the static type of E1, which is D. And then we want to see if it's an ancestor or a descendant of G. So D here is an ancestor of G, because we can just go down like that, which means that this is a downwards cast, and the typecast is going to compile. Now we want to see, does the assignment compile? So we know that for the typecast over here, we're making an alias with static type G. And this G1 variable has static type G as well. So in this case, it will compile because G is a descendant of itself. So overall, this is going to compile. However, what is going to happen during runtime? So during runtime,
Attendant, pause. Okay. Anybody would like to give a try? Since this might be the first time you're seeing this, right? Give it a try, right? As if it's a test question. What's going to be the output at the runtime? Think about it for a moment. I think it might be better if you think about it, before we tell you the answer. Yeah. It compiles, but what's going to happen at the runtime? So runtime, you may want to look at dynamic type, right? Yeah, give it a try.
So you will give the class exception.
You will give a class cast exception. Why?
Yeah, because we cannot jump from E, because that's the dynamic type of E1 to G.
Okay, pretty good. So in this case, your fellow student said exactly right. So E1 here is still pointing to the E object. So dynamic type for E1 is E. So we're asking, can the dynamic type of E1, which is E, can it fulfill the expectation of the cast type, which is G? In this case, no, you cannot, right? Yeah, so this will be kind of the rule check you have to get more used to, especially for tomorrow. So I would say Tian Tian actually gave these two examples very great, as an extra. So definitely go over them and just get yourself familiar about sometimes, whenever you talk about compilation, only look at the static type. When you have to analyze the runtime behavior, then you have which version of the method should be called, or should there be any class cast exception? You have to look at the dynamic type, right? That's a principle, right?
okay. So those are all the examples. I also have some summary notes here if you guys want to look at it.
Tian Tian, why don't you go over that with them?
Okay,
Yeah,
I'll go over them
with
as
us.
well, I guess.
Yeah.
Okay, so for typecasting, as we just went over, to check for compilation, we want to check if the static type of the variable that we're casting is either an ancestor or a descendant of the cast type. So in that case, if it is an ancestor or a descendant, the cast is going to compile. But to check the entire compilation, you need to make sure the rest of the line compiles as well. However, if it's not an ancestor or descendant, then there's going to be a compilation error.
Just some very quick clarification, just in case you're wondering. So the way Tian Tian put it here is asking whether the static type of the variable is ancestor or descendant of the cast type. In the class, I put it another way. I said, is the cast type ancestor or descendant of this variable? the static type. They are really the same expression. They're really the same. So all you gotta do is look at the static type and the cast type to see whether you're doing an upward cast or downward cast. That's the main thing you want to be able to do. Okay. And also, when we show the diagram there about given the Java class declaration, you want to visualize the diagram like drawing the arrows. Make sure you double check the diagram before you actually start answering question. I can tell you that there will be multiple questions there tomorrow that will share the same diagram. You definitely don't want to use the wrong diagram, to actually answer the question. Always double check. Okay.
So that's for compilation. And then for runtime, we want to check, is the dynamic type of the variable that we're casting a descendant of the cast type? So for compilation, we're checking the static type, and it just has to be an ancestor or descendant. But for runtime, we want to check the dynamic type, and we want to make sure it's a descendant of the cast type. So another way you can think of it, it's almost equivalent to assignment, where we're checking the right-hand side if that's a descendant of the left-hand side. So we're checking if the right-hand side is a descendant of the left-hand side. So it's like the same thing with assignments, where we're checking if the right-hand side is a descendant of the left-hand side. So this is like a general rule that you can go back to in case you forget. So in the case that it is, then we'll create an alias with the cast type. However, if the dynamic type of the variable is not a descendant of the cast type, then there's going to be a class cast exception. So that's for typecasting. And then I have notes here for variable assignment as well. So when we have a new object, then we're going to check if the dynamic type is a descendant of the static type. So again, we're checking if the right-hand side of the assignment is a descendant of the left-hand side, which is equivalent to saying, does the dynamic type fulfill the expectations of the static type? And then when we have an object reference instead of a new object, we want to check static type. So is the static type on the right-hand side a descendant of the static type of the left-hand side? So in both cases, if the answer is yes to these questions, then it will compile. If it's no, then it's not going to compile. Okay, and finally, we have method calls. So for compilation, we want to check, is the method defined in an ancestor of the static type? So what that means is if we go back here, let me find a good example. Let's say this one. So we want to check the static type of the variable, and in this case we have D. So we're checking the static type, and we're going to check, is the method defined in D, or is it defined in some ancestor of D? And that's basically saying, do we expect D to have this method? Is this method part of the expectations for D? So in that case, if the method is defined in the static type or some ancestor of the static type, then it'll compile. If it doesn't, then it's not going to compile.
So Tian, maybe here you want to say ancestor of the static type of the context objects. So that I think that'll be a little clearer. You can just write it here. So yeah. So whenever you get a method call, so to judge to see if that will compile, look at the left-hand side of the dot, which will be the context objects, and figure out its static type. And then does a static type can be expected for the method you're calling. That's basically what you're checking. Yeah.
Okay, so then for runtime, we always want to check dynamic type. So we're checking, basically, we're going from the dynamic type. So if we go back, we'll do this one. So basically, we're starting from the dynamic type, which is E. And we're going to check, does it have the method? If it does, we call it. If it doesn't, we go up a level, go to the next ancestor. And we check, does it have the method? And if it does, we call it. Let's say F did not have BM defined. Then we would go up another level and check D. And we would check, does it have BM? If it doesn't, we go again up and check The next one, does it have BM? And again, if BM is not defined in F, then we would call BM in C. Does that make sense? That's basically it, I believe. Yeah, that's it. Do you guys have any questions?
Yeah, that's great. So guys, any questions to follow up on any of the practice questions or any concept you want to clarify? Yeah, Patricia, go first. Yeah.
So let's say I have a C object and like I cast an alias and it's just casting to itself C. Is that upcasting or downcasting?
Okay. Are you okay? So if I understood you correctly, let me add a new page here. Are you asking, let's say, if I got C and then obj new something, and then I try to do cast maybe obj to just C?
Yeah.
Okay, it's a good question. I would say it's more like a special case, right? You can argue either way to say it's a downward, upward cast or downward cast because a class is simply its ancestor and descendants. You can say either way in this case. But the expectation after this will just remain the same. Okay? So this one you can think about because static type is C, you're cast to C. So you can think about it's more like a upward and downward cast at the same time, which means you're not going anywhere really. Yeah, you can say both. Okay. Question? Yeah, you're fine. Okay, I think we'll pause the recording right now.